Okay, so in this video, I would like to prove that the function e to the x is a convex function. So first of all, let's recall that the definition of a convex function is it's a function f such that if I pick any two real numbers, u and v, then I always have that f of lambda u plus 1 minus lambda v is less than or equal to lambda u plus 1 minus lambda v. Okay, and this is for any parameter lambda that is strictly between 0 and 1. So for reasons that you can consider yourself, this basically means that the function is always sitting below its secant line. So for example, if I draw the graph of a convex function, it's going to look maybe something like this. And if I draw a secant line between any 2 points, the function is always sitting below this secant line. And it turns out that this kind of geometric property is equivalent to this definition right here, or this inequality. So what we're going to do in this case is we're going to use an equivalent property of convex functions. So I'm going to use the following property. So I'm going to claim that my text box is going to disappear. Okay, so I'm going to claim that a function f is convex if and only if its second derivative is greater than 0. And this is a semi-difficult analysis proof. You can try it for yourself if you want. You have to use certain expressions involving the second derivative and then something called the Taylor expansion for the second derivative. So we're not going to get into that here, but in this case, we're just going to note that if I take the second derivative of e to the x, well, what is that? First derivative of e to the x is e to the x, and then the second derivative of e to the x is e to the x. And it's definitely true that this is greater than 0, so that means it immediately follows from that e to the x is a convex function. So this is a pretty straightforward exercise, and I think it just serves as a good review of the definition of convex functions. And yeah, that's it.